So this video is going to be looking at component 2, so section 2.2 lesson 1 on data transmission. So if we were in school, we would be raiding Aladdin's cave, otherwise known as Moz's cupboard, to find out all his old kit, and would have been having a look at these different types of cables here. That's because the first part of the lesson is going to be to describe serial and parallel transmission and the advantages and disadvantages of each one. So if I flick back to that image, you can see that these big thick ribbon-like cables here, they're parallel cables. Now most of you perhaps haven't seen those before, but that's how we used to connect lots of different devices, especially things like printers. We're then going to go on to have a look at simplex, half duplex and full duplex, and explain how multiplexing affects data transition rates. Now they sound like wrestling moves, but I'm assured that they're not, and that it's something to do with data transmission. So serial and parallel transmission then. So when we're transmitting data, we can either send it in serial, which is where one bit follows another bit and they all go down the same piece of wire, cable, or we can send it in parallel, where we can send multiple streams of data down multiple wires. Now initially, parallel sounds a lot better because you seem to be sending a lot more all at the same time. However, there are disadvantages, and that's perhaps why we don't tend to use it as much. So that's what we're going to have a look at now. So an advantage then of serial transmission is that you only need one wire. That means that you can reduce the amount of physical space that the cables take up. So if you remember those ribbons from that image, they're actually quite big, and that takes up space. You know, you're not really going to want those inside a mobile phone, and it's also going to reduce the cost because you don't need as much physical equipment or physical components. So it might appear that it could be slow, however the clock that's used to control how fast the data can be sent can be increased so that you can send more data per unit of time. It's good for transmitting over longer distances, as something called synchronization is not an issue. So synchronization, when we're using parallel, means that all of those bits need to be arriving pretty much at the same time along each wire. And if you're sending over a large distance, that sometimes gets a little bit out of sync, and that causes delays, bottlenecks and problems. It's used in USB devices and transmission between other devices. So USB the S stands for serial, so Universal Serial Bus. Okay, so that's what the S stands for there. So parallel transmission then, it used to be used, it says here, early parallel communication systems were faster than serial links. However, you could get an issue with something called crosstalk. So because the wires in those ribbons are quite close together, you can get sort of interference between the two wires, and that causes obviously issues where the data gets corrupt. So you did tend to get some issues there. It would reduce the signal quality if you got any crosstalk. They are found in integrated circuits, buses with inside computers where it's a short distance, and where synchronization problems are going to be less likely. There's something called skew, where bits can travel at different speeds over each of the wires, which is obviously going to be a problem because it's going to make the data out of sync when it arrives at where it's supposed to be going. So going to put on a little video now following this one that explains it in a little bit more detail with nicer graphics than I can provide.
USB. One of the wonderful conveniences of modern life. You just plug it into any one of the similar looking ports and things just work. Well, most of the time anyway. But whatever happened to those old school massive things we used to use to connect printers and hard drives? Well, older standards like IEEE 1284 and IDE cables had so many pins and took up so much physical space because they communicated in parallel, meaning that they could send and or receive multiple bits of information simultaneously. By contrast, new school interfaces like USB, SAS, SATA, and individual PCI Express lanes are serial, which, fun fact, is actually what the S in each acronym stands for. These ones can only send or receive one bit at a time. But wait a minute. Why on earth would that be better? I mean, when they close all but one lane on the freeway, that's a bad thing. Well, popular parallel standards had a number of limitations that slowed down their real-world speed. These ports depended on all of the data lines sending the correct data simultaneously. So trying to push more and more data through a parallel port per second means that it's harder and harder for those lines to stay synchronized, meaning that as you increased the data rate, the port actually had to slow things down and wait for all of the signals to match up. Another phenomenon called crosstalk also complicated matters. Crosstalk is basically electrical interference between data lines that are close together, and it becomes more pronounced when you add more lines than again when you try to make them faster. Because a serial connection like USB only has one data line in each direction, crosstalk isn't nearly as much of an issue. This means that although serial connections can only fire off one bit at a time, the rate of fire can be made much higher, especially as electronics manufacturing in general has improved. So think of an automatic machine gun shooting tons of bullets per second, one at a time, versus a break barrel shotgun that can fire lots of pellets at once, but has a much longer reload delay. Parallel connections also had the disadvantage of using lots of pins to support transmitting multiple bits at once, and that meant that the connectors themselves were more prone to damage. Think about how easy it was to bend printer pins or an IDE header on an old motherboard. Modern serial links typically don't use protruding pins, making standards like USB and SATA suitable for, many more insertions, as they say. But Linus, hold on a minute. What about my fancy new graphics card that uses 16 PCI Express lanes at once? Isn't that parallel? Well, not really. Each PCI Express lane has its own clock signal, so they're not synchronized with each other. The data is simply transmitted down each lane in a more independent fashion, leaving the card itself to sort out the information, which doesn't take very long, meaning that PCI Express speeds scale very well as you add more lanes, which you can see in high-speed PCI Express devices like solid-state drives and video cards. Pretty incredible, right? Well, that may be. But as far as one bit at a time serial technology has come, I wouldn't bother trying to eat your bowl of Frosted Flakes one at a time.
Okay, so moving on then to the second part of the lesson, we're going to be having a look at simplex, half duplex and full duplex data transmission. So when a network's set up, it needs to be decided sort of what protocol is going to be using, and also whether or not the media is going to be using simplex, half duplex or full duplex modes. So as you can see from this sort of set of three diagrams, simplex, this is where data can travel in one direction. Half duplex, data can travel in both directions but only one at a time. So it can only go one way at a time and then it has to swap to go the other way. And full duplex, this is where data can travel in both directions at the same time. So an example of simplex transmission would be with a satellite, maybe for satellite TV. So the data can only be sent in one direction, so that's from the satellite to your TV. You can't send signals back to the satellite. Okay, so when you're watching TV, if you're watching Sky, that uses simplex because your satellite on the side of your house receives the data, but you can't send messages back. So half duplex transmission, this is, as we said, where you can send data in both directions but only one at a time. So if you think of a walkie-talkie, you can only speak one at a time. So when you push the button to talk, the data's going from your device to the other device. They can't talk back at that same time, they can only listen, and then afterwards obviously they can then respond to you, and the transmission switches over. Full duplex, as we said, this is where the data goes in both directions at the same time. So we're thinking of things like a twisted pair cable such as Cat5. You can have data for uploading data and downloading data, so like two sets of cables, and also then the data doesn't interfere with each other because it's not using the exact same piece of wire. Thinking of telephone calls, for example, you can both speak and hear at the same time, talk over each other, so therefore that's using full duplex mode. So in summary, duplex or full duplex means that it can go both directions at the same time. Half duplex means that it can go both ways but only one at a time, and simplex is only in one direction. So that brings us on to the last part, which is multiplexing. So network links, so we're thinking of cables, Cat5 cables for example, fibre optic cables. They can support a wide range, usually a certain range of communication frequencies or channels, and that's also known as the bandwidth, and it represents the total theoretical data carrying capacity of the medium. So you get different gigabit possible transmissions using different cables. So multiplexing allows independent data sources. So if we're thinking of like 30 computers connected via one fibre optic cable, they can combine their communication just using that one fibre optic cable. They don't need a cable each, so they're all transmitted over the same wire or medium simultaneously or seemingly simultaneously. So that's called multiplexing. So 30 computers all using one fibre optic cable. That fibre optic cable has to be split, not physically, but split so that all 30 computers can access that communication medium. And you can see at the bottom there some other examples. You've got radio frequencies, cables, which we mentioned, optical fibre, fibre optic, which we've also just mentioned, and all of those are capable of multiplexing. And there's a couple of types that you need to be familiar with. So the first one is FDM, frequency division multiplexing. So it's an analog technology, and it divides the bandwidth in logical channels and allocates each user a channel. So each user can use the channel frequency. So maybe if it's being transmitted over radio waves, you get a certain frequency, each user does, and you can have 100% access then to that channel. You've got exclusive access to that channel. Interference is avoided as you've got a suitably large frequency to send your data over. So you've got your own frequency, someone else has got theirs, etc. And that's how you can transmit using FDM. The other one is TDM, which is time division multiplexing, and this is where each user can only send data over their specific time slot. Now, if you're using a high bit rate, which you would do, it doesn't feel like your data's being split up into different time slots. Actually, when you put it all over that high bit rate, it seems seamless. So the diagram kind of explains this one quite nicely, I feel. So the digital signals are converted into frames, so you can see there the red, the green and the blue, assuming that you don't struggle with colours. Red is here at the top, we then have green in the middle and blue at the bottom, and then as they're transmitting across this one cable, you've got green, then red, then blue, then green, then red, then blue. And it seems then when you pick them up that your data's come through seamlessly, but actually it's been split up into different frames. So that concludes 2.2 lesson 1. The PowerPoint for this is in the department shared area, which you can get to from the Arthur Terry website. Any questions, we will be on Teams, but hopefully that explains it quite nicely. You just need to make some notes essentially on your OneNote.